Right. So thank you today for coming this seminar. So speaker is Ziyu Huang, who was originally working at USC under Dr. Joe Wang, who has expertise in plasma dynamics, I believe. There, he was working in numerical simulations, particularly using molecular dynamics simulation code, who you're working with Dr. Nakano as well, right? So they have a very strong expertise in numerical simulations, and he has a lot of into it. Later, he moved to Boston University to serve as postdoc for a year, and now he's joining my lab. My expertise is basically planetary science as well as astrodynamics. His expertise is more like space physics, so I have to learn from him. But I'm really excited to have him because he can characterize high-speed impact of particles or high-energy particles on lunar surfaces, other terrestrial planets. So I am very much looking forward to his talk, and let's see. All right, take over. Thank you.
Thanks so much, and thanks for having me here, and thanks for the great introduction. I'm very happy to join Georgia Tech. Get to know a lot of planetary scientists over here. Just moved here a few weeks ago, but I can feel this is a really nice place to do space explorations because we can combine science and engineering perfectly. Okay, so a little bit about me. I study the moon, Mercury, Europa, and also more recently, I also studied some research on exoplanets beyond our solar system with different shapes and different colors and all kinds of possibilities. Okay, I'm gonna start with our closest neighbor, moon, in particular, the journey of finding water on the moon. So you see here on Earth, water is basically everywhere, but when we look up at the moon, we don't see any of those similar features and signatures of water. And as a matter of fact, for a really long time, we believe that the moon is totally dry without any water molecules. So it's quite boring to a lot of scientists, especially for astrobiologists, because everybody loves the moon. We even have an International Observing the Moon Day last week. But unfortunately, if it's totally dry, it's quite unlikely to have life here. So, and what is more interesting is that this time range even covers the great Apollo mission area. So if you think about it, those water molecules are really playing hide and seek with those astronauts on the moon. But the great thing about Apollo mission sample return analysis is that it started like a few decades ago during the Apollo missions, and it's still continuing right now. Like here, we have a survey node, and a lot of scientists are actually performing analysis for those actual lunar samples from Apollo missions. And because the science question is sitting here, but the technology of solving those science questions is rapidly being developed. And there's a study in 2008 that totally reshaped our understanding of the moon's history by obtaining the existing evidence of water on one of the lunar samples. And then later in 2009, some really exciting discoveries was made by spacecraft like Chandrayaan-1. It was actually not designed to find water on the moon by this mission, but it did detect signals of possible hydration features in some of the regions that we see. And the big question still hold because we cannot distinguish whether the signals from MQ mission is attributed to hydroxyl or actual lunar water molecules. And in October 2020, SOFIA, which is a telescope on an airplane traveling in the stratosphere, made a groundbreaking discovery confirming the existence of water molecules at 6 micrometer band. And these are also on the sunlight surface of the moon. So this suggests that water may exist more widely across the lunar surface, not just in the permanent shadow regions. And also the abundance is way higher than what we thought it would be before. So, okay, so with all of those conformations of lunar water, and now we can really start to think about where do these water molecules come from. Okay, so there are many proposed mechanisms that contribute to the formation of lunar water, like volcanism, outgassing, comets, meteorites, solar wind. But if you look at the space environment around the moon, solar wind particles, micrometeors, and energetic ions or electrons are able to directly reach the lunar surface. So this motivated me to think about, start looking for evidence that how this unique space environment shaped the evolution and formation of lunar water columns. Okay, so when I really started to look for where to get started, the very first reference I found is the global solar wind-induced water cycle from Brent Jones from Georgia Tech. And in particular, the lunar water cycle starts with proton implantation, where proton combine with oxygen from the regulus, and then the hydroxylated surface can then undergo photostimulated desorption or second-order recombinant desorption, eventually become water molecules. So when I was looking at this network and thought, how those reactions reach like K1, K2 up to K6 can be derived, and how they're connected to the space environment around the moon. Like when there's a solar storm, how the solar wind velocity affect the proton implantation step, and how could the micrometer impact velocity enhance or reduce the retention of water formed by the second order recombinant desorption. And these are all strongly related to the dynamics of those processes. So here's when I came across reactive molecular dynamics simulation. Well, the name is basically like a self-introduction. RMD is a first principle-based modeling method that simulates the interaction between items. And the time evolution of the position of each item is solved by integrating the equation of motions, which is the dynamic part of the simulation. And the interactive potential between items are controlled by the calculations of bond order, Coulomb forces, and these are essential to simulate chemical reactions, like simulating the bond breaking and forming process. Okay, so with this powerful tool, the first prospect we looked at is solar wind implantation, which is again the very first step in the whole network. And most of the previous investigations are experimental studies. Well, if you look at this summary table, this kind of like ion radiation experiment started from like tens of 20 years ago, and it's still continuing right now. But the conclusion about whether solar wind implantation contribute to the formation of hydroxyl or water molecules are not the same. And we believe there are two reasons in the experiment. First of all, the energy of the beam is not strictly 1 keV like following the actual solar wind conditions. You can see there like the most energetic beam can be like 100 keV, which is so high. And second, the flux used in most of the experiment is orders of magnitude higher than the actual lunar conditions. And this could possibly lead to continued heating of the samples. And water as a volatile species is very, very sensitive to those thermal changes. So in our simulation, we aim to critically follow those two important parameters. We focus on the case, again, within permanent shadow regions, when there's no photo desorption and the temperature is relatively low, like 40 Kelvin. So the thermal desorption is minimum as well. And we calculated the velocity for solar wind based on the local plasma conditions. And most importantly, after each implantation, we manually relax the surface to the original temperature, ensuring there's no energy residue before the next implantation. So this will eliminate the effect for continued heating. And here we are saying that most of the hydrogen items are from solar wind are turning to hydroxyl groups and molecular hydrogen, with very few of them getting to water molecules directly. And although this, with more implantation, the number of molecular hydrogen is continuing growing, the number of hydroxyl on the surface becomes stable. So this is corresponding to the saturation features found in most of the previous experimental studies. And what our simulation can tell further compared to their experimental studies that if the implantation continues, those H items from solving are likely turning to H2 molecules instead of OH or H2O significantly. So this could possibly affect the efficiency of turning solving hydrogen into actual lunar water. And this will also prevent those hydrogen take a part into this global lunar water cycle. Okay, so, and then we continue to simulate the most promising mechanism to generate water molecules from hydroxylated surface, which is micrometer impact. There are actually very few studies investigating this process because, first of all, it's very, very difficult to achieve this hypervelocity, like 10 kilometers per second or even 20 kilometers per second. And second, the chemical reactions occur in a time scale of nanoseconds, which is extremely hard to capture in a laboratory setting. In 2019, Zhu and others used a carbon dioxide laser to simulate the impact. And this is a quite exciting experiment. They qualitatively shows that the formation of water and even they're accumulating on the surface after the impacts. So this also motivated me to simulate this process through reactive MD to get more details. So here, so we used these samples that was previously done in the previous section, which is solving implantation. And after the saturation is achieved, we use this sample to make a larger sample. And what you're seeing here is a 16 kilometer per second impact. You can see the ejecta produced by this micrometer impact as well as the formation of quasars. So that is quite similar to a large scale impact. But the good thing about R&D is if you look closer, reactive MD can actually track the exact trajectory for the items that actually made these particular water molecules. Like the one shown on the right, we highlighted the hydroxyl group and a hydrogen atoms. And once the impact is happening, we have this white line showing the trajectory. The heating by the impact enabled the diffusions of those hydroxyl and hydrogen atoms, and then water molecules formed and then released from the surface. So this enables a comprehensive analysis of the reaction pathways during all of those like planetary processes. And the impact also removes those hydrogen items on the surface. If you see this top view, you can see this like especially the structure change at this impact site, and also removal of possible volatiles and hydrogen items. And the amorphous structure make it possible to deposit more hydrogen items and increasing the potential for water molecules formation during a second impact. So this leads us to think about the combinated process of solar implantations and micrometer impacts. So in the implantation simulation, we identify a saturation features, and based on the local number density of solar vein and permanent shadow regions, and also the velocity, we can derive a time scale for this maximum saturation time saturation of implantation, which is in the order of like 1,000 years. And we also use two classical models to estimate the time scale for micrometer impacts, which is one of them is a function of micrometeor flux models, and another one is the affected area of craters created by a certain particle radius and impact velocity. And then by integrating over the whole mass range of the meteorite and also the velocity range with a distribution function of the impact velocity, we can achieve a time scale for micrometer impacts in the order of 10 to the power of 4 years. So if the time scale of micrometer impact is larger than the saturation time scale of implantation, which is actually the case we found for permanent shadow regions in our simulations, all the hydrogen after the saturation time and before the next impact, which is shown in this blue shaded region, they will either be reflected or turn into H2 molecules and leave the surface. In other words, this part of the hydrogen may not be part of the water formation cycle network. And the efficiency of converting solvent hydrogen to water is relatively low. But they are also important for the H2 cycles, which is also quite interesting topics. And additionally, we noticed another process that is quite unique, and usually only occurs at permanent shadow region, which is dielectric breakdown. So dielectric breakdown occurs due to this extremely high energy particles like SCP event, solar energetic particles event, or cosmic or galactic cosmic ray event. And if the temperature of the regulus is extremely low, like 40 Kelvin again, then the electrical conductivity will decrease exponentially. It's shown here. And at permanent shadow regions, and the discharge time for those ions could be up to days because if your electrical conductivity is like really low, then the time scale will also grow exponentially. So this actually set up a perfect condition for those ions to be accumulated, and then a strong electric field will build up if there's a density difference for those ions. And again, we use an updated version of reactive MD simulations with polarizable charge model. And this can simulate the response of materials and any kinds of setup under a strong electric field. So we use the electric field estimated by the previous like Jordan's model of deep dielectric breakdown, which is 5 times 10 to the order of 6 volts per meters. And once again, we show that applying the electric field and also turning it off, cool down to 40 Kelvin, we found numerous water molecules on the surface. And there are even some ice structures because we found some hydrogen bonds connecting those water molecules, which are extremely exciting. And the reason I found this exciting is also by estimating the time scale as we compare the implantation and impact. So previously we compared this, the combination for solving, I got this. All right. Combination of solving and impact. And we found that at permanent shadow regions, the time scale for implantation is up to 1,000 years, and impact is 10 to the order of 4 years, like 10,000 years. And now based on the JPL SCP models and GCR fluence models, and we can estimate the time scale of dielectric breakdown for typical permanent shadow regions at 40 Kelvin to be the order of 10 to the order of 3 years, which is close to the saturation of implantation. So this is about 1 orders of magnitude smaller than the time scale of impacts. But this actually makes a difference between permanent shadow regions and non-permanent shadow regions. So it's totally possible by looking at this time scale, within PSRs, implantation and breakdown are likely responsible for the formation of lunar water rather than solar implantations and micrometer impacts. This unique combination facilitates the formation of water since, again, the overall timescale is 1 order of magnitude smaller, and also dielectric breakdown may even occur on an unsaturated surface, which has a higher efficiency of converting hydrogen to the water molecules. So continuing on this topic, during my stay at Boston University Center for Space Physics, we further combined this MD simulation with global simulation of slowing interacting with planetary bodies, and in particular, like some magnetized or weakly magnetized bodies like Mercury. And we're currently trying to figure out how the magnetosphere that changes with the interplanetary magnetic field would explain the observed dynamical sodium exosphere. And also for the asteroid Psyche, the most recent James Webb observation have found some 3 micrometer features on the surface, potentially due to hydroxyl, just like the hydroxyl we have seen on the lunar surface. So again, how did they get there? It's a metal body. But this magnetosphere modeling and the test particle trajectory can actually give you an answer for that. And even for paleomagnetosphere, how the ancient solar wind of Earth's wind interact with the moon. Like a few billion years ago, here I put this title, when the moon had a magnetosphere. This work is mostly done by my undergraduate research assistant, Jackie. And in particular, we are focusing on different isotope ratios compared to the current solar wind and how differently they are implanted to the surface because of this paleomagnetic field. And most importantly, how they are evolving with the changing of liquidity of the moon and also geophysical process like meteor impact. Okay, now move a little bit further away. Our investigation of water also expand to these icy moons, for instance, the Europa. And actually, Europa Clipper mission is scheduled to be launched next month. So fingers crossed and no more surprises, please. Um, so previously, for the measurement and collection of dust, this is always a challenging task from my perspective, especially for water ice, because again, it's volatile and upon hypervelocity impact, the ice cream will rapidly fragment and vaporized or even ionized. So this is also a challenge for this cosmic dust analyzer when measuring those ice particles in the ring of Saturn. So understanding the fermentation of ice cream and their hypervelocity will provide it's kind of like a theoretical base for interpreting the upcoming data from SUDA, Europa Clipper mission, and possibly from previous data from Cosmic Dust Analyzer. So, and now this is a, it's not showing very well, but this is a 4K rendered video. It cost me a lot of GPUs to do this video, showing the fragmentation process of a single water molecules under 6 kilometers per second. We set up a surface at the bottom, simulating the detector surface, and generate a bond that hold those water molecules together based on the hydrogen bond order calculations. And these hydrogen bonds are actually essentially the major reasons that we have a lot of water clusters in the fragments. And it's also pretty commonly seen in the previous ice impact experiments from this mass spectrometer. But here we are generating what we call this a pseudo mass spectrometer. We're not like analyzing the mass of the molecules or atoms. We're sampling the cluster size, like the number of atoms in a cluster. Essentially, those 3 N beams represents mostly water clusters, like H2O, H2O2, up to a few like large cluster. And here I'm comparing a moderate impact with 800 meters per second impact on the top, and there's a 6 kilometer per second impact on the bottoms. And but just looking at these fragmentation patterns, there are distinct differences to be noticed, like the mixing beings for H2O and +1 or -1 for the upper panel. And this is attributed to the covalent bond energy of OH inside a water molecules. So we have identified a velocity threshold for interatomic fermentation or intermolecular fermentation. And this again is an example of how the dynamics, like the velocity, impact velocity, affect the chemistry as well as the fermentation patterns we see for this type of velocity impacts. Well, the interatomic fermentation part is still under review. But for the intermolecular fermentation, we have noticed something that was overlooked for a long time, which is the effect of water clustering on the impact generated exosphere modeling. So this figure shows the ejecta after an ice impact containing like single water molecules or even larger water clusters, and the figure on the right is color-coded by this kinetic energy, like the velocity of those molecules clusters. So you can see this large cluster has significant lower energy compared to other like smaller single molecule or single clusters. So based on this observation, we established a mixed Maxwellian distribution considering the cluster size. And here's a direct comparison for the single and mixed Maxwellian distribution. And I'm also plotting the black dashed line, vertical line, which indicates the escape velocity of those planetary bodies. So below the escape velocity, water molecules or water cluster will remain gravitational bounded and become part of the surface water in the exosphere. Additionally, this velocity distribution will also be useful for estimating the scale height of this exosphere, which is extremely important once we get the in situ measurement of those icy bodies. The most obvious difference we can see is that for Europa-like icy moons, the previous exosphere model will underestimate the amount of surface-bounded water molecules by a factor 2. And for smaller bodies like Enceladus, the difference could be 10 times. So which should really be taken into considerations when modeling the impact generated exosphere for those icy moons, especially when we have data. Yeah. Okay, now we're heading to exoplanet atmosphere. If you were here last week, you will definitely find this schematic plots very familiar. It was so funny that I didn't know Xinting was coming because I was not on the astrobiology email list because I'm pretty new here. But for those of you who missed last week's talk, basically Xinting proposed a framework or a models to tell whether the exoplanet is Jupiter-like with a deep atmosphere without a surface, or the atmosphere of the exoplanet is a Titan-like with a shallow surface. And essentially, the idea is that the high pressure and high temperature condition for deep atmosphere will recycle those photochemical models on the top. But those with a shallow surface, they won't. And a perfect example in Xinting's paper in 2021 is K218b. So what's interesting about K218b is that it has been previously observed in the 1.1 to 1.7 micrometers range with Hubble telescope, WFC3. And for a really long time, the retrieval shows that this range of the signal is because of the H2O, water. But due to the degeneracy between water and methane in this range, we don't actually know whether it's methane or H2O rich atmosphere. But when GWST data came in with better quality and obviously broader spectral range, we now realize that the previous absorption is due to methane and the amount of H2O is very, very limited. So, and we went back to the surface problem paper in 2021 and which assume is water rich, figuring out what could be the case. And again, when we think about our planet Earth, one thing that was obviously pop up to our height is like the condensation of water. So here, we apply different albedos, assuming if there's a cloud and the thickness of the cloud, the level of the clouds, and we calculate the pressure, temperature profile, and we notice that water actually start to condense over this range, the cross section of the saturation vapor pressure curves. And well, we are running the simulation for K218b, another cool planet jump up to our reading list, which is LHS 1140b, and it turns out to be very, very interesting again when the GWST results are out. And if you compare the pressure temperature profile, it's even colder for LHS 1140b compared to K218b. So water are further condensed out. And the most obvious difference when we consider water condensation is that at some levels, like around 1 bar to 0.1 bar, when the temperature is like low enough, mixing ratio of water will drop significantly from 0.1 to about 10 to the order -5. And because water are likely the dominant oxygen carrier in the atmosphere. So this basically changes everything. And this is the complex photochemistry model. But I was told by Xinting that nobody's gonna read this spaghetti plot, even as a reviewer. So let's turn into this colorful spaghettis into something we can actually see by GWST. Oh, there's more, sorry. Yeah, okay, so which is the transmission spectrum from those spaghetti, and along with the GWST data in green, HSD data in red, and also SPITher in purple. So the condensation did help to explain the depletion of water, especially the missing water water features by other spectrum, and also a deep atmospheric condensation. With condensation is likely able to explain most part of the spectrum, but it's still not good enough to explain the 1% methane and carbon dioxide. And we have basically tried most of the scenario we can think of, and so this will point to the possibility that there's an ocean for this K218b, and there's some floods of methane and carbon dioxide that make up this atmosphere. So maybe it's like a secondary atmosphere as a possibility. So this basically come out to the supercritical water phase, the upcoming work by Cindy students, and I'm sure more exciting data from GWST. We also provide more information about this mystery planet. Okay, so except for this atmosphere-rich planet, I was also involved in some analysis of rocket planets as well. And the most popular system, TRAPPIST-1 system. So we have in GWST cycle 1, we have the secondary eclipse measurement of B and C. It's pretty safe to say that B has little to no atmosphere. And even and for C, there's basically no thick atmosphere. But again, the data quality is not good enough to exclude some of the scenarios. But and quite recently, we have a chance to observe the combined phase curve of TRAPPIST-1B and C in GWST cycle 2. We got around like 72 hours, which is almost the largest program dedicated to one system. And from this GWST phase curve, this is basically the first GWST phase curve, summer phase curve of temperate terrestrial planet. And again, they reviewed no thick atmosphere around TRAPPIST-1B and C. But again, this paper is currently under review. I can't talk too much about that. But there's one particular thing that I found really, really interesting to this community, and especially for planetary science community. We are reducing and analyzing the data, which is I know a lot of like astrobiologists and exoplanet scientists will be quite disappointed if there's no atmosphere around the planet. Just like when they hear there's no water on the moon. But even if it's an airless bodies, the secondary eclipse data and the phase curve we just got is still very, very valuable in a way that we can understand its surface evolution and also the space weathering we're talking about. For instance, there are some analysis introducing comparing like the strong space weathering effect or weak space weathering effect. In particular, this none-of-this iron, which are largely found in the lunar samples. And also they are assuming it to be Mercury-like exoplanet. They even add some like graphene, like 1%, 5%, even 0.1% graphene in it, and just to see how it change the modeling of the thermal emission. And not only the single data point like this one we got from secondary eclipse, now we have the whole phase curve to better quantify like what kind of space weathering effect this airless bodies is experiencing, and we're gonna have more phase curve again to better understand the evolution and composition of the surface. And now this really brings back to the title of my talk, which is From the Moon to Exoplanet. We have found those none-of-this iron in lunar grains due to space weathering several years ago. And now this could be very, very useful to understand how those airless bodies lose their atmospheres and when they get started to generate its secondary atmosphere. If you think about the planet Earth, Mars, and a lot of like solar system bodies, we have secondary atmosphere. And we have lost most of their H2, like predominated atmosphere. And in particular, right now at survey, I think we are trying to figure out the separate effects of, first of all, like ion radiations or micrometer impact and how they're contributing to the different size and distribution of this none-of-this ions with this actual return samples from Apollo missions. So I guess with the correlation of none-of-this iron contents, we can date back to estimate the stellar wing properties of exoplanet system as well, which has never been done before. And if you think about that, this is quite challenging. And unless you send a spacecraft to this exoplanet system, you can actually measure the stellar wing. But yeah, and the other part of my title, you couldn't find a better time to talk about this because to better understand the world we're living in right now and the other world we can see by GWST, because we are in the era of Artemis and GWST. So I'm pretty sure that the synergy between this planetary science, heliophysics, and exoplanet can give us a better understanding in the context of computational chemistry and computational physics. And with that, I will take any questions you may have. Thank you.